thanks a lot, everyone. It's my great honor and pleasure to be here. I'm a professor in computer science at UC Berkeley and also the founder of a startup called Oasis Labs. Today, I will talk about towards building a responsible data economy. As we all know, data is a key driver for modern economy. And the data helps us to make better decisions and provides a huge value for us. However, and also more and more data is being collected every day. And there's estimates that a significant percentage of EU's GDP comes from value from personalized data. And the global data economy is growing exponentially. However, a lot of this data is sensitive. And we are facing unprecedented challenges in how sensitive data is being used for both individuals and businesses. For individuals have lost control over how their data is used. Oftentimes, their data actually has been sold without even their knowledge and awareness. And oftentimes, the data is being sold under the premise of anonymization. However, as research has shown that anonymization is not sufficient to protect user privacy. So what you are seeing here on the screen is a study showed by New York Times, which showed that from mobile phone location datasets, anonymized mobile phone location datasets that they were able to obtain from third party, which is often easily accessible from third parties, they are actually able to track the location of a Secret Service agent with the former President Trump. Hence, you can actually see the trajectory of former President Trump. So this is a great example showing that anonymization is insufficient to protect user privacy. And also oftentimes, when data is being sold, users are not getting sufficient benefits from their data. And for businesses are also facing huge challenges when handling sensitive data. Large corporations are still facing huge data breaches. For example, in many of the recent attacks, attackers were able to steal sensitive information of hundreds of millions of users or even billions of users in the attack. And also regulations like CCPA and GDPR are making a good first step in setting up privacy protection regulations. But however, at the same time, they are becoming costly and cumbersome for businesses for compliance. And more importantly, the biggest issue is that a lot of the valuable data is actually being locked up, being put in data silos that's now being utilized and make it difficult to actually utilize and extract value from the data. And also as new technology being developed, they can unlock utility, but also oftentimes at the cost of privacy, as demonstrated by the recent controversy in using facial recognition software for law enforcement. So overall, we are facing tremendous challenges in how we handle sensitive data and how we best utilize this data. And we are at a state where the problem as the digital economy moving forward and becoming more and more prevalent, it's only these challenges are only going to get more and more severe. And it's at a point where if these challenges are not addressed, they will hinder societal progress and even undermine human values and fundamental rights. So we have an urgent need for a framework for a responsible data economy. So what do I mean by a responsible data economy? There are a few goals and principles of a responsible data economy. First, we would like to maximize data utility. We would like to utilize the data and extract value to help individuals, organizations, governments, and societies. And at the same time, we need to establish and enforce data rights. As we utilize data at the same time, we need to protect users and organizations of their data rights. And this will form the foundation of data economy and can help prevent misuse and abuse of data. And also, we want to have fair distribution of value created from data. And this can help optimize for economic welfare and improve economic efficiency. So how do we achieve a responsible data economy? We need to set up a comprehensive framework for a responsible data economy. The problem is very complex. First, there's natural tension between utility and privacy. On one hand, we want to get as much utility from data as possible, but on the other hand, we need to protect the sensitive data, protect users' data privacy. And also, data, when compared to physical goods or physical objects, data has a unique property called non-rivalry. For a physical object, for example, when I hold a laptop, then I'm the only person who can hold this laptop. Nobody else can hold the same laptop at the same time. And this is called rivalry. However, data is different. When I hold a piece of data, somebody else can hold a copy of the same data. And hence, data is called non-rivalry. And hence, we cannot simply copy and copy concepts and methods in the analog world to use in the digital world. And because of this complexity, to address this, to enable a responsible data economy, it requires a combination of technical and non-technical solutions. In particular, a framework for a responsible data economy, as I outlined here, has 3 key components. One is the technical solutions to build a technical foundation for a responsible data economy. And 2, we need a legal framework to support a responsible data economy. And 3, we need to have novel incentive models to incentivize users and society to build a responsible data economy. In the rest of this talk, I will summarize and briefly talk about each of these components. So first, let's look at the technical solutions. So far, traditional solutions are insufficient for solving these problems. So the traditional solutions use data encryption, but usually only use data encryption for data at rest or in transit, and hence only protect data at rest or in transit. And data is either not used or once used is often copied, and hence making it difficult to control the usage. When somebody uses the data, they get a copy of the data, but once they get a copy of the data, the original data owner essentially loses control of how that copied data will be used in the future. And also, as we have already seen, anonymizing data is insufficient to protect data privacy. And thus, we need new technologies that can provide new capabilities. In particular, we need to protect data when data is in use. And in particular, we want to provide controlled use of data without needing to copy the raw data. And also, we need to protect the computation outputs from leaking sensitive information as well. So luckily, in the research community and also now in industry, we have been making rapid advancements in an area I call responsible data technologies. So these are technologies that support and enable responsible data use. There are different types of responsible data technologies to help address different aspects of data protection when data is in use. So here I list 4 different types of technologies. The first one is called secure computing. So these include secure hardware-based approaches and crypto-based approaches with the goal to keep data confidential during compute. So to protect the computation process from leaking sensitive information. And the second technology is differential privacy, which prevents computation output from leaking sensitive information. And federated learning helps to keep data on users' devices will enable, for example, machine learning models to be trained in a distributed manner. And with distributed ledger, it helps provide an immutable log to ensure users' data rights and users' policy of how data is being used. So now let me talk about some of these component technologies. So first, let me talk about the secure computing technologies. Again, the goal of these secure computation technologies is to protect the computation process from leaking sensitive information. So one way to think about this is essentially to compute over encrypted data so that the entity that's carrying out the computation actually does not see the raw data. So this type of technology has mainly two types of approaches. One is cryptographic-based approaches using, for example, secure multi-party computation, homomorphic encryption, and so on. And another type is utilizing secure hardware. So for cryptographic-based methods, for example, homomorphic encryption and MPC, secure multi-party computation, these fields have made tremendous progress in the past. For example, here on the slides, I'm showing some of the recent work in using homomorphic encryption for neural network inference and training tasks. So just in the last several years, already the performance for homomorphic encryption-based methods for neural network inference has improved by 2 orders of magnitude due to the novel technical contribution from the research field. However, it's still, in general, difficult to be practical. For example, the homomorphic-based methods are still too slow for large network inference and currently are impractical for training even for small network. For example, the best technique using homomorphic encryption-based methods for doing training on MNIST will still take 8 days. And okay. And performance on secure multi-party computation and PC methods in certain cases can provide better performance. For example, for 2 PC based methods, you can do inference on ImageNet with the ResNet 50 architecture, but it still takes over 500 seconds per instance. And the training is too slow even for small network. And with 3 PC performance, it's better, but still it's 2 to 3 orders of magnitude slower than the native computation on CPU. And for training a VGG16 network, it will still take more than 7 years. So to summarize, these cryptographic-based methods, they can be practical for certain use cases, but however, they are still impractical for more data-heavy applications and more general purpose tasks. And with the secure hardware, the advantage of the secure hardware is the performance is close to native, and hence it can support general purpose computation. So with the secure hardware, essentially the goal is to build a black box, often called a secure enclave, which provides isolation, where the program, the data essentially are put in this black box and being executed in this black box, which is done using a combination of hardware and software solutions. And the outside operating system and applications will not be able to see what's running inside the secure enclave and will not be able to modify what's running in the secure enclave, and hence provide strong confidentiality and integrity. And also, secure hardware can provide a capability called remote attestation to enable a remote verifier to verify that verify the program running in the secure enclave and its initial state, and hence verify the computation correctness of the program. So secure enclave essentially can serve as an important cornerstone security primitive given its strong capabilities. And it can provide a platform for building new security applications that couldn't be built otherwise for the same practical performance. Given its importance, different hardware manufacturers have all developed their solutions for secure hardware. However, all these solutions are closed source. So there are many challenges in building a secure hardware. How secure can it be, and what threat models? And what would you entrust with secure hardware? Your Bitcoin keys, financial data, or health data? And the ultimate question is, can we really create truly trustworthy secure enclave as a cornerstone security primitive, such that when widely deployed, it can enable secure systems to be built on top? If we can achieve this, this will enable a new secure computation era for the whole community. So what's the path towards a truly trustworthy secure enclave? First, I believe it needs to have an open source design. Open source design provides the needed transparency and to enable high assurance. And also open source design helps build a community. And also, ideally, we would like to have flexibility and extensibility to support diverse use cases. And ideally, we would like to provide formal verification of the design and implementation of the secure enclave. And also, we would like to have secure supply chain management for the secure hardware manufacturing process. Towards addressing these goals, at Berkeley, we have been developing the first end-to-end open framework for secure enclaves called Keystone. Keystone provides a simple abstraction by utilizing hardware capabilities, memory isolation capabilities, building directly on top of RISC-V, which is open source RISC architecture. And it has a modular and flexible design to enable extensible functionalities. And given its modular and flexible design, it has a minimal trusted computing base and make it much better suited for formal verification. And also, Keystone not just enable one open source design of a secure enclave. It actually provides a framework for designing customizable TEs, trusted execution environments. With its modular and flexible design, Keystone enables a rich framework that enables both the platform provider and enclave developer to customize what primitives and guarantees a TE should employ. Similar to a software, essentially similar to the software design network, software-defined network. With our prototype implementation from the experiment results, it shows that Keystone has very low performance overheads. Essentially, it's for most applications has almost negligible performance overheads comparing to native computation. And you can actually try out Keystone on the latest RISC-V boards and also on FPGAs with emulation using KMU and so on. And with Keystone and open source secure enclaves, we have been building a community together, and Keystone has now become part of the Confidential Computing Consortium, founded with a number of leading technology companies. So that's the first component technology, secure computing, with the goal of protecting the computation process from leaking sensitive information. And hence, we can protect the privacy of data while data is being used. However, secure computing alone is insufficient to support responsible data use. We also need other component technologies. Another aspect that's also very important is that we also need to ensure that the computation output doesn't leak sensitive information about individuals. So to see that, let me show you a motivating case study. As we all know, neural networks has high capacity. So the question is, do these neural networks remember training data? And if they do, can attackers actually exploit this vulnerability to extract the secrets in the original training data from just simply querying the learned models without even knowing the details of the learned models? And if the attackers can do this, there are many risks for such training data extraction, including enabling attackers to learn sensitive information about users' data, and also enable attackers to actually use data outside of its intended context. So breaking contextual integrity of data. So in our recent work, in collaboration with researchers from Google, we look at one task, which is training a language model. So with training a language model, the goal is by training on the text corpus, the language model can provide a prediction in the following way. When provided a sequence of words or characters to the model will then try to predict the next words or the next character. And for example, if you have been using Smart Compose in Gmail and so on, essentially that's the language model is trying to do the smart composing. So in one example case study that we showed is that we consider the following learning task where we train a language model on an email dataset called the Enron email dataset. The Enron email dataset naturally contained the actual user's credit card and social security numbers. We show that when we train a language model on this email dataset, an attacker, without knowing the details of the language model, without knowing the architecture, without knowing the parameters of the model, but an attacker with only query access to the model, by devising new attacks, we show that an attacker can extract the original user's credit card and social security numbers embedded in the original training dataset. And this is an example illustrating that even as we train machine learning models, we need to take precaution to protect users' data privacy. And we also propose a measure called exposure to measure this type of phenomena called memorization. And this type of measure has helped with data privacy in Google Smart Compose. And also more recently, in collaboration with researchers from Google and elsewhere, we have explored a similar question for training data extraction from even much larger language models, in particular, in this case, GPT-2, one of the largest language models. And by devising new attacks, we show that similarly, one can extract sensitive data used in the original training data from just querying the model without knowing the details of the model. So for example, here are examples of personal identifiable information that's being extracted from these new attacks from GPT-2 model. And also here's an example showing a slightly altered memorize the contents, showing that actually one can, from just creating the model, can extract the following, essentially the following storyline. It's essentially a jury summary, but however, actually with the wrong person's name. And this can even cause other legal and privacy questions as well. So these examples show that even as we train machine learning models, it's important that we take precautions and approaches to protect users' data privacy. And luckily, in this case, so in certain cases, we have good solutions. So in particular, when the language model was relatively small, we can actually use differential privacy to help protect users' data privacy while still maintain a similar utility. While the solution currently gets more challenging with the increased size of a language model. So what is differential privacy? Differential privacy is a formal notion of privacy. One way to think about it is here, when we talk about differential privacy, we can consider two neighboring data sets where one data set has one more point than the other. So for example, here, Joe's point. And we consider randomized algorithm is differentially private when we run the algorithm or when we run the query on these two neighboring data sets. The resulting output, the probability distribution of the resulting outputs are very close, are very similar. So intuitively speaking, this means that by just looking at the output, an attacker will not be able to tell whether Joe's data has been used in the computation or not, and hence help protect Joe's data privacy. So data privacy is a very powerful notion, but however, there are many challenges for practical use and deployment of general purpose differential privacy for data analytics and machine learning. In particular, we need to have good usability for non-experts. Most data scientists and machine learning researchers and practitioners are not aware or familiar with differential privacy. And we also want to have broad support for analytics and machine learning workloads. And we want to have easy integration with existing data environments. However, previously, no existing system can address all these issues. So in our recent work, we developed a framework using program rewriting to automatically rewrite analyst queries to automatically embed differential privacy mechanisms and other privacy mechanisms into the original query to create an intrinsically private query, such that this rewritten query, when run on the original database without any modifications, can automatically provide differentially private results. And hence, with this program rewriting approach, we can make it really easy to deploy differential privacy, where the data analyst does not need to know about privacy at all, whereas this program rewriting framework can automatically select the best differential privacy mechanism to embed for a given query and automatically produce differentially private query results. And also in our recent work, we developed new techniques, in particular for a high order language and linear type system for statically analyzing and verifying differential privacy guarantees of machine learning algorithms and automatically derive differential privacy bounds. And our derived privacy bounds in certain cases can be even tighter than certain manually derived results. And the work has won the Distinguished Paper Award at top programming language conference. And also, these techniques and tools have been deployed are in pilots in industry, and we hope that differential privacy as an important component technology to enable responsible data use, in particular to protect computation outputs from leaking sensitive information about individuals, can become more and more widely deployed. So far I've talked about these two component technologies, secure computing and differential privacy. And factor learning can help enable that data doesn't need to leave the owner's devices, and while enable machine learning models or data analytics can be done in a distributed manner. So for example, machine learning models can be trained in a distributed manner. And also with the distributed ledger, it can provide an immutable log to ensure users' data rights and enforce users' policy for how its data should be used. So given interest of time, I won't go into these two other component technologies in more detail. When putting these four component technologies together, it helps build a secure distributed computing fabric to serve as a platform for a responsible data economy. And this platform for responsible data economy can also enable some new capabilities. And this is also something that Oasis Labs, we are pioneering and piloting as well. So in particular, these component technologies, when putting together, can enable a new type of assets that I call data assets. In particular, when we combine secure computing and blockchain, it allows a new paradigm for data assetization and data tokenization. In particular, blockchain allows for logging and enforcement of users' rights to data and their usage policy for data. And blockchain provides an immutable log with high integrity and auditability. And with the secure computing, it ensures that the data remains private during compute and cannot be reused without permission. And when we create a capsule of data and policies combined together, this helps to create an asset called the data assets that can be consumed along specific guidelines also for specific exchange of value. So with data tokenization, we are building an Oasis platform that can help unlock a new responsible data economy where individuals can maintain data rights and earn value from their data assets. As a concrete example of how such data assets can help users and how such a platform can enable this new type of capabilities, here we have been developing technologies, in particular in the domain of protecting users' genomic data. So a number of direct-to-consumer genomic analysis companies have recently cited slowdown in consumer demand, largely due to privacy concerns from consumers. With the Oasis platform, and also with this platform of responsible data technologies, essentially we can enable users to take control of their genomic data and become owner of their genomic data. Users can specify how they want their genomic data to be used. For example, they can give consent to a genomic company to do genomic analysis on users' data. And the genomic company, in this case, can only use the user's genomic data for genomic analysis inside a secure execution environment. And hence, the genomic company cannot take a copy of users' data, for example, to sell the data without users' consent. And this way allows users to still maintain control of their genomic data and at the same time to enable their genomic data to be utilized in a privacy-preserving way, and also potentially gaining value, even monetary value from that data. For example, as pharmaceutical companies utilizes users' data and give royalty or other rewards in return. So far I've talked about the first component of a framework for a responsible data economy, the technical solutions. And now let me briefly talk about the next two components. So first, let me talk about the incentive models. Essentially, in order to build a responsible data economy, we need better incentive models. In particular, how do we determine and distribute value of data? And in our recent work, we show that for machine learning domain, we can treat this as a collisional game. And we show that an approach sharply value can actually provide the unique and only solution that satisfies a collection of desirable properties. So the existing data valuation approaches are often ad hoc and insufficient. For example, they may be flat rate pricing, or they may be based on auctions, or there are also machine learning models based on data attributes for pricing. But however, in general, they are ad hoc and do not really contribute a value to each data contributor properly. So when we look at the data valuation, there are a number of requirements for the desired data valuation scheme to satisfy. One, it should be task dependent. Data only has a value when used, and essentially the value of the data depends on the task it helps to fulfill. For example, the medical data for a particular disease may only be useful for that for diagnosis and drug development for that particular disease, and will be much less valuable for other medical procedures and so on. And also, the data valuation should be cumulative. The value of the data should accumulate when used for different tasks. And it's interdependent. The utility of one data source hinges on other data when jointly used for solving a task. For example, again, a medical data for a particular patient from a big population may be much less valuable when there are other similar patients in the data set, whereas a patient's data for a rare disease can be much more valuable. And also, the data valuation scheme need to have fairness. Data's value should be should fairly reflect the utility of the different data sources. So given these requirements, essentially, with our recent work, we show that machine learning can be essentially modeled as a collisional game, where the data distributors are players in a collision, and the usefulness of the data essentially is characterized by the utility function. And given this problem setup, our recent work showed that essentially the concept of Shapley value, which was originally proposed by Lloyd Shapley, a Nobel laureate for Nobel Prize in economics, this Shapley value defines a way for distributing the profits generated by the collision of all players. And our work showed that Shapley value actually provides the only distribution that satisfies the collection of desirable properties that I mentioned earlier. And Shapley value essentially can be defined as So there's a Shapley value that we can define for each player, and in this case, essentially each data source, where the Shapley value is for a player of a particular data source is defined as the marginal utility contribution for this player or this data source when computed as expectation for all subsets. Of players, excluding this particular player. And when Shapley value, when we utilize Shapley value defined this way, it essentially satisfies a number of properties, including fairness, group rationality, and cumulativeness. And so our work showed that essentially Shapley value provides a rigorous foundation and framework for essentially determining and distributing individual data contributors' value from a trained machine learning model. But however, as you may have seen here, Shapley value, the computation can be very expensive. The complexity of computing exact value of Shapley value is combinatorially is exponential. And this is particularly expensive when in machine learning context where the data set can be very large. And in our recent work, we also have developed various methods for more efficient algorithms for computing and approximating Shapley value for different types of machine learning algorithms. So due to time limit, I won't go into more details for this second component of the framework for a responsible data economy, the incentive model. So now let me quickly touch on the third component, the legal framework for a framework for responsible data economy. So privacy laws have been proposed around the world. However, there's demand for more effective regulation for privacy protection in general. And in particular, there are very important open challenges. For example, what are data rights and who controls data rights? So for example, individual property rights have only been actually developed and enforced in recent history. And individual property rights have since become a cornerstone of modern economy. Individual property rights helped establish modern economics and fueled centuries of significant growth. Similarly, when we look at not physical property, but digital data, today we lack an adequate framework for data rights. And establishing data rights will allow individuals to derive value from their data and propel economic growth and unlock new value. And there have been many diverse concepts and frameworks proposed for data, how to view data rights, and so on. And it's a great field and great time to explore these questions and concepts. And in general, we need data-driven and technology-informed regulation. For example, how will advancement of responsible data technology influence and impact regulatory frameworks? And also, how can regulation help with faster, broader adoption of responsible data technology? So COVID has forever changed our lives. And data, of course, is critical in fighting the pandemic in many areas, including contact tracing, including developing drugs, better diagnosis, medical care resource prediction, and so on. But however, there are a lot of challenges for handling sensitive data in fighting the pandemic. Oftentimes, it's difficult to get data in a timely fashion, and there are many privacy concerns. What data is collected by whom, how long will the data be stored, and how is data used? And in general, we need this framework for a responsible data economy to help better fighting the pandemic. So with the whole community, I hope that together we can build a future of responsible data. And here I have a few predictions that I would like to share. So these are 10-year predictions. So in 10 years, I believe that secure computing will become commonplace. For example, in 10 years, most chips will have secure enclaves capabilities to enable secure execution environments. And in 10 years, most computation will use secure enclaves and happen in secure execution environments. And also in 10 years, we will see crypto accelerators for cryptographic-based secure computation methods to become commonplace. And in 10 years, data trusts and data commons will become predominant. So in 10 years, data trusts and data commons will become predominant ways of utilizing diverse sources of data, enabling ownership economy where users benefit from their data as owners and partners. Unlike today, oftentimes users are essentially the product of services. And in 10 years, data stewards, fiduciaries, and trustees will be a new class of entities important in the data ecosystem, managing and protecting users' data and growing its value. And in 10 years, huge economic value will be created through these new forms of data trusts and data commons, orders of magnitude higher than today's marketplace. And in 10 years, most large corporations will have chief responsible data officers. In 10 years, most companies will have responsible data as an important function to ensure digital stewardship and responsible data use, and have chief responsible data officer as an executive role. And in 10 years, most companies will be monitored, audited, and rated on their responsible data use, similar to their environmental impact. In 10 years, many common practices today will be banned. For example, in 10 years, fine-grained targeted advertising will be opt-in only. And in 10 years, the sale of anonymized data without user consent will be banned. So to summarize, I've talked about the challenges that we're facing today with the use of sensitive data. And if we don't address this problem, essentially the problem will only get more and more severe, and it will significantly hinder the economic growth of the new digital economy. And hence, for the future of the internet, we must build a responsible data economy. And with the whole community, let's build this together.